And you are of course most welcome. This is Project Euler problem number 26. Reciprocal cycles. A unit fraction contains 1 in the numerator. The decimal representation of the unit fractions with denominators 2 to 10 are given. Now when you see brackets here, that means it's a repeating cycle. So 1 over 3 is just 0.3333 recurring, so it has a repeating cycle of 1 digit. 1 over 7 is 142857 recurring, so it'll just go with those 6 digits infinitely. So here's the question: what is the value for the denominator under 1000, which gives the longest recurring cycle? So here is how we calculate the recurring cycle of a number. So let's do 1 over 22. 1 divided by 22. So first thing we do is divide 1 by 22, which doesn't go. So we have a quotient of 0 and a remainder of 1. Pay close attention to the remainders, they are very important. So we have 0. Now we take the remainder, multiply it by 10, and make that the new numerator. 10 divided by 22 is still 0, remainder 10. Take the remainder, multiply by 10. 100 divided by 22 is 4, remainder was 88, so 12. 120 divided by 22 is 5, remainder was 110, isn't it, so 10. 0.45, there we are. Take the remainder, multiply it by 10, and now we've actually hit a remainder that we've already used before, so now we're just going to enter an infinite cycle. So 100 divided by 22 is 4, remainder 12, which 120 divided by 22 is 5, remainder 10, and 100 divided by 22 is 4, remainder 12, and it'll just go on like that forever. So 4, 5, 4, 5, 4, 5, 4, 5. So 22, 1 over 22 has a cycle of 3 digits before it will start recurring. So if we put in 22 as the function input, we should get 3 as the output. Excuse me a second. Okay, so with that in mind, let's code the solution. Once we have found a remainder that already exists in our list of remainders, we stop the program and return a value. So let's get rid of paint. There we go. Right. From time import perf counter as p, and then start equals p. There we go. Just saves time having to type out perf counter every time. Def get cycle length for the denominator. Right, so we start with numerator, which is always 1, and we start with an empty list of remainders. Once we find a duplicate in our list of remainders, we immediately stop and return a value. So while, and the easiest way to check if your list contains duplicates is to get the set of the list. That removes all the duplicates, and then you compare the size of the list and the set. If they're the same, there are no duplicates. If they're different, there are duplicates. So while length of remainders is equal to the length of the set of remainders, then we simply iterate as I just described. So remainder equals numerator mod, missed it twice, numerator mod denominator, then remainders dot append remainder, then remainder equals numerator No, it's not. It's the other way around. Numerator equals remainder times 10. And that will do it. So then we return the length of the set of remainders. There we go. Let's test it out with a couple of values. We'll test it out with 22. We know that 7 has a recurring cycle of 6, so we'll test that one as well. I'll do a few more. 7 should have a recurring cycle of 6. 3 should be 1, but I don't know if my code works for very small numbers. We'll just have to see. What else? What else? Let's try something like 113 and 45, something like that. Right, I will get rid of Chrome so we can all see. Boom. Yep, that seems to work. 22 had a recurring cycle of 3, 0, 4, 5. 7 is something like 1, 4, 2, 8, 5, 7. 3 has a cycle of 1. 113 has a cycle of 112. That's a very interesting property, which we will come back to later when we look at the clever solution. So let's just get rid of the brute force solution first. So we need some variables first. So longest cycle and biggest denominator, set them both to 0. For I in range, I'll start with 2 and go up to 999. Python's awkward. And then current cycle equals get cycle length of I. Then if current cycle is bigger than longest cycle, then biggest denominator equals I and longest cycle equals current cycle, and that will do. So then end equals p, just to get the time, and then print. We want the biggest denominator and end minus start. Print that off. Oh, I've spelt something. Yeah, there we are. Mr. T. There we go. And that gives the correct answer in 0.734 seconds. I think that's a bit slow, given that we only had 998 numbers to check. So we're going to look at something a bit cleverer. So we're actually going to go back to the whiteboard for this bit, which is just going to have to be wiped. Yep, okay. So let's bring that back up. There we are. And I've put my tablet away, which I shouldn't have done. Right, let's have a look at 1 over 7. Because like several numbers in our list, it has a strange and useful property. Okay, 1 over 7. 1 divided by 7. So, let's have a go. So, 1 over 7 is 0, remainder 1. 10 divided by 7 is 1, remainder 3. 30 divided by 7 is 4, remainder 2. 20 divided by 7 is 2, remainder 6. 60 divided by 7 is 5, remainder 4. No, it isn't, it's 8, remainder 4. 40 divided by 7 is 5 remainder 5. And then, what else have we got? 50 divided by 7 is 7 remainder 1. Now we've already had a remainder of 1, so we are done. And that is the reciprocal cycle for 1 over 7. Now, we actually used all possible remainders in this algorithm. So there's 1, 2, 3, 4, 5, and 6. You can't have a remainder of 7. And if you have a remainder of 0, your algorithm just stops because you don't have a repeating cycle. You have just a finite number. So, for a denominator d, the maximum repeating cycle is d minus 1 digits. Here it's 6. The maximum is always d minus 1. So, but only some numbers have this property. And as you may have guessed, they tend to be primes. In fact, they are primes. But not any kind of prime. So I'm going to get rid of this. Oop. And we're going to do a bit of internet searching. I'm going to bring up an article I found on Wikipedia. Let's bring it back up so you can see. There. It's called Repeating Decimal. This is the article we want. And we're going to go, this is all maths language, I don't really know what it means, but section 3 is very useful. So again, lots of maths stuff here. So we're going to scroll down. So one particular paragraph that I found particularly useful. Here we are. If a prime p is both full reptend prime and safe prime, then 1 over p will produce a stream of p minus 1 pseudo-random digits. So those are the types of primes we're looking for. Now quite often what you'll find with Project Euler is the key to solving the problem quickly is not actually to use the standard algorithm. It's actually just to find something tangentially connected to it and use that. So what we're going to do is we're going to find all the primes below 1000 and we're going to sieve them down. So just build a list of candidate primes that fit the bill. So they have to be, what did the article say? They had to be both a full reptend prime and a safe prime. So we're going to take a list of primes. I'm actually going to load in the code for problem 7, which has a sieve of Eratosthenes. So we're going to get all the primes below 1000 and just whittle them down. So I'm going to modify this slightly so that we can actually have a list of prime numbers, not just a list of booleans. So return I for I in range 2n if primes I. That will do. Right, I want to do the timer again. So from time import perf counter as p, then start equals perf counter. Oh no, p. We're also going to need to install import is prime. So from simpy import is prime. If you don't have simpy, there are plenty of primality tests out there on the internet that you can borrow. So let's get our list of primes. So list of primes equals sieve limit, and I'll set the limit to 1000. Limit equals 1000. There we go. Now we got our list of primes. Now we need to whittle this down to a list of safe primes. I'm going to move this up. So safe primes. What is a safe prime? Okay, so a prime number p is a Sophie-Germain prime if 2p plus 1 is also prime. Okay, so the number 2p plus 1 associated with a Sophie-Germain prime is called a safe prime. So 11 is a Sophie-Germain prime because if you multiply 11 by 2 and add 1, you get 23, which is also prime. 23 is the safe prime, and 11 is the Sophie-Germain prime. So what we need is to sieve this list of primes into a smaller list which are safe primes. So here we go. Safe primes equals I for I in list of primes if is prime, and then what are we doing? It's I minus 1. We gotta kind of inverse. We've got to do the inverse of the equation. So if we want to know our number is a safe prime, we have to subtract 1 and then divide by 2. So I minus 1 divided by 2, and I'll just make sure that BidMass is properly enforced because I don't trust Python. There, I think that should do it. Oh, doesn't like it. Oh, yeah, there we are. It's just that. Cool, right. So now we've got a list of safe primes. What on earth is a full reptend prime? Right, full reptend prime. A full reptend prime or long prime in base B is an odd prime number such as the Fermat quotient gives a cyclic number. This is going to be a bit of a problem because B is the base, so that's 10. We're raising it to something like 997 and then dividing by 997. I think that's going to give a bit of a problem. I don't think Python can actually handle that. What if we do mod? Okay, let's do mod. Right. What are we gonna do? Yes. Okay. So full reptend primes equals I for I in list of primes. Did I fully explain what a full reptend prime actually is? I don't think I did. Okay, so we have this equation here where B is the base. We're working in base 10. It's raised to the prime minus 1, and then we subtract 1 from that, and we divide it by the prime. Now, if the result of this is a whole number, then it is said to be cyclical, and therefore one of the primes that we're interested in. If we get a floating point number, if there's any remainder, then it's not full reptend prime. So I for I in list of primes, if, oh blimey, I, so it's 10 to the power of I minus 1 minus 1, and that's going to be all in brackets, mod p equals 0. That should work. And then, now we've got the full list of candidates, we simply take the largest of them and print that as the answer. So end equals p, and print max full reptend primes and end minus start. Hopefully that has worked. Oh, doesn't like it. Okay, what have I done? built-in function, or oh, I've done p. What have I done p for? That should be I, shouldn't it? Try that again. 997. Well, that's wrong. That shouldn't be list of that should be safe primes. This is embarrassing, but yeah, it's too late in the day to stop and start again, so let's try that. There we go. Boom. Correct answer in what have we got? About 2,000ths of a second. That'll do. So we got there in the end, didn't we? So that's it for today, and I will see you next time for problem 28, because problem 27 is already up. So see you then. Okay, I just realised you can't see all the code, so I'm going to get rid of Chrome, and we're just going to run the thing again. So here we go. Just to show you I'm not kidding you, there we are. So that's it, and as I said, I'll see you next time.